Hello everyone, welcome back to alkaline hydroxide 784, and this is the mathematics series, and this episode we are going to be covering the first part of vectors, which is called basic properties of vectors in 2 and 3 dimensions. Yeah, it's too long, never mind. Anyways, I'll just look at the syllabus stuff, because if I say my own things, I'll probably tell the entire chapter of vectors and that would not end well. It will take too long. So I'll just follow the syllabus points and talk accordingly. Okay, so before we start, you should know what is a vector, obviously. And if you had a physics lesson before, you would know what a vector is. A vector is something that has both magnitude and direction. And later you will get to understand how this works in the mathematics topic of vectors. But in physics, you would know that, for example, if you're talking about the difference between distance and displacement, it is the fact that distance is a scalar and displacement is a vector. So because distance only has the magnitude of distance, and let's say if you're in a circle, like if you're in a circle, as long as you're at any point of the circle, the distance is the same. But for displacement, whatever point you're on and on that circle, it'll be a different displacement because the direction is different. So very first thing that you can do with vectors is to add or subtract them. And it is fairly easy, especially if you have your bracketed vectors or your IJK kind of vectors. And from there you just, for example, if you have your vertical bracket x, the x thing in the y one and the z, so you just minus accordingly, and you just do this addition and subtraction for each line and write a new vector based on that. And likewise for the IJK, you just minus the IJKs individually, and then you get your resultant vector in not resultant, you get the vector that comes out of adding or subtracting these two vectors. Okay, so um okay, so the next thing that you can do with vectors is to multiply a vector by a constant, which, for example, if you want to find this vector times 2 or by times 3 or something like that. So if when you do that, you can just multiply the individual numbers in it by that same constant and it would work. So that's pretty straightforward as well. And then the next thing that we've written here is a geometrical interpretation. Basically, when you add two vectors, imagine two lines, like, as I said, like displacement. So the first vector would be going in one direction and the second one would be going in the other direction. So the addition of the two vectors would be like, for example, if the first one starts from point 1 and ends at point 2, and the second one starts from point 3 and ends at point 4, point 2 and it ends at point 3, the addition of both vectors will give you a vector that starts from point 1 and ends at point 3. And for subtracting vectors, it is different, because instead it will be like you have the first vector starting from point 1 and ending at point 2, and the second vector starts at point 3 and ends at point 2. So it's like you're going the opposite direction, so you end up going from point 1 to point 3 again in this scenario. I think the picture would be more obvious than my explanation. And then for the multiplication, is like, if you go to PowerPoint and you have a line, then you copy paste and attach it on that line. That's basically what it looks like. Very simple, nothing hard. Okay, so the next part is about the notations. So the different kinds of notation. The most familiar one is the one with the bracket. I don't know whether it's the right way to say it. It's like the matrix kind of notation. So you would have like a big bracket and it will be vertically either xy or xyz, depending on whether it's 2D or 3D vectors. Yeah, it's pretty straightforward. And then the other kind of notation that would be presented in questions mostly is the IJK system. So if it's only x and y, you have I and j. If there's a z, then you have k as well. Do remember to draw the squiggly lines on the I, j and k because they are vectors, so you must draw squiggly lines on them because you can draw bolded letters very obviously in the sense. In a document or something they can be bolded, but when you write it you must write the squiggly line on top. So without the x or the y or whatever, the I, j, k are actually unit vectors in the direction of the x-axis, y-axis and z-axis respectively. So that's how they work. The other way of representing vectors is, for example, you have 2 points A and B and there's a vector in between them, then you can write A, B with an arrow on top. That shows the direction of the vectors from A to B as in a sense, but you won't really know what is the actual numbers, like you don't know the x, y, z of AB unless you write that down specifically. But you can say AB is equal to the x, y, z or x, I, y, j, z, k, whatever you want to do. And another way of representing AB is maybe with something like vector A. In this case you must write the squiggly line on the A or whatever letter you like to use for your vectors. Maybe you just don't use IJK because you could be confusing it with the IJK obviously. Yeah, so that's the various notations that you can use. And afterwards, so the next point is about the various kinds of vectors per se. Okay, so position vectors, which basically the position of the vector with respect to the 0 point. I think what they're trying to cover here. I don't know. Displacement vectors, you have the position with respect to the 0 and you also account for the magnitude or something. And the direction vectors is the direction part. So technically like the position and the direction makes your displacement, I think. I don't know. um yeah. But direction vectors do not have to be the exact same vector as the position. Like for example, if your vector A is 1, 2, 3, your direction, okay, actually not 1, 2, 3, you should call it maybe 6, 8, 10, maybe 6, 8, 10. Your direction vector can be what? 3, 4, 5. It's the same thing, but yeah, it's the same direction. It doesn't have to be the same so-called length as the actual vector. And then the next one is the magnitude of vector, which is pretty simple. If you use Pythagoras theorem, this is like an extended version of Pythagoras theorem, because if you want to know why this works, imagine in a cube. In this case, you're using a cube, so like our space is a cube. For 2D, it's pretty obvious, like you can just use the Pythagoras theorem. For the 3D, you can still technically use the 3D version of Pythagoras theorem, because if you think about it, like you imagine the one face of the cube has x and y, and you can find the distance for that. And now you have that line and the z, so you can use Pythagoras theorem on those two lines again, and you will get the final answer. So in this case, you can just do it directly and then find the square root of x squared plus y squared plus z squared. I mean, yeah, like just do that and you get your distance. Yeah, but before you actually get the distance, sorry, this is a magnitude, sorry. This is a magnitude of the vector. So then the next point is the unit vector. So the unit vector is like IJK. They basically have a magnitude of 1. So they can be whatever xyz you want, but they must have a magnitude of 1. That's what a unit vector is. And they can come with a hat instead of a squiggly line on top. Yeah. So for example, if you have vector A, if you put A hat, that is the unit vector of A. So then the distance between 2 points, basically you first subtract you subtract the 2 point, like one point from the other, and you can find the magnitude of that vector, and you get the distance between 2 points. And then afterwards you have the direction cosines. For the most part you won't really be tested on them, but it's easier to draw it than to actually see it. So imagine you have a point, your vector point, you have x, y, z, and from there you can find the direction cosines using a formula, which I will write down here because I don't really know how to say it in a nice way. But the point is, there's the direction cosines in the x, y, and z directions. Yeah. So the next one is collinearity. This is pretty simple to prove. Basically just prove that, for example, if you have two different vectors, first make sure that they're attached to each other, obviously. They have a common point. Then see whether both the vectors are parallel to each other in a sense. Like one of them can be a multiple of the other or something like that. So once you prove that, you can say that they're collinear. And finally, the ratio theorem, which is probably the most interesting thing in this chapter. I mean, this part of the vectors chapter, I guess. Basically, the ratio theorem is quite interesting because it just simplifies things in a great extent. So I will write it down here because I don't want to say it out and accidentally say it wrongly or something. It's easier to write it down. And the proof will be right here. Yeah, if I have a proof, I'll just show it to you. If I don't, then I don't know what I'm gonna do. Yeah, the point is you can use it if you have like a line AB and then there's a point in between C. You can find out what is the, like if you have the ratio of A to AC and CB, you can find out what 0 to C is. Like for example, if you're everything starting from origin, you can find out what OC is. So yeah, that's the idea. And yeah, there isn't anything else much to say because this is the first part of the vectors. The more interesting things come later. And I have nothing else to say. If you found this useful, even though I probably wrote down some of the stuff, please press the like button and subscribe. And with that, I would like to say thank you and bye. Sorry for the bad editing. I mean weird editing because I talk too fast for my writing. So if you have problems viewing the collinearity thing, just pause it the video at that point. Good luck with that. Okay, bye.